Hello, I'm Mavromatis, and today I'm gonna talk about using virtual reality to unlock intuition about non-Euclidean geometries. I am working in France with VR experts and a researcher in geometric groups theory. Let's dive right in with a minute of context on non-Euclidean geometries. Non-Euclidean geometries are geometric systems that deviate from the classical rules of Euclidean geometry, which is the geometry of the plane, which you probably learned in school. Non-Euclidean geometries, by contrast, allow to model curved or distorted spaces. In Euclidean geometry, if one walks without ever turning right or left, the trajectory is a straight line. In spherical geometry, it would be a great circle. And in hyperbolic geometry, it would be a hyperbola. These non-Euclidean geometries are obviously of interest to mathematicians in the field, but not only to them. They can be used to describe real phenomena, such as routes for which the shortest path is not a straight line, and are used in a variety of scientific fields: computer vision, computer graphics, and, perhaps more famously, to describe the space-time continuum. Before these geometries can actually be explored in virtual reality, they must first be simulated. Conventional rendering engines cannot simulate non-Euclidean geometries since light no longer travels in a straight line in these geometries. It travels along an equivalent, geodesics. It is therefore necessary to develop a simulator that sends light along geodesics. This is what we did, based on a previous project led by Rémi, which renders geometries using ray marching. In 3 dimensions, there are 7 non-Euclidean geometries which coexist with Euclidean geometry. For the work I'm presenting to you today, we focused on S2 cross E, which is difficult to compare to Euclidean geometry due to its structure. S2 cross E is the product of a sphere and a Euclidean line. Or, to make a more interesting division, it is a space which sections are spheres, S2, or cylinders, S cross E. In S2 cross E, geodesics, that is, straight lines, are either great circles around the S2 component, straight lines along the E component, or curves spiraling around the S cross E component. Understanding complex mathematical structures often requires years of formal education and abstract reasoning skills. Among these, non-Euclidean geometries pose particular challenges due to their counterintuitive properties and limited visualizability in everyday experience. These geometries, especially in 3 dimensions, are typically introduced only at advanced stages of mathematical education. Yet, as I showed you, non-Euclidean geometries are not only of interest to mathematicians and play a fundamental role in many fields of science. Furthermore, engaging with these geometries can foster a valuable shift in perspective, encouraging learners to question deeply held intuitions about space, logic, and truth. For these reasons, it is both intellectually and practically worthwhile to develop alternative ways of accessing and understanding such geometries, especially for non-experts audiences who may benefit from them in interdisciplinary contexts. At the same time, VR has emerged as a promising tool for education, offering immersive and interactive environments that can support experiential learning. Prior research has shown that VR can enhance learners' spatial reasoning, engagement, and motivation, particularly in mathematical domains. While several studies have explored the use of VR in teaching mathematical concepts, and others have addressed pedagogical approaches to non-Euclidean geometries, relatively little work has been done at the intersection of these 2 fields. Based on these observations, we designed an experiment which goal was to explore the possibility for users to develop an intuitive understanding of S2 cross E through virtual reality without knowledge prior to the experiment and without using any mathematical formalism. Our objective was not to teach advanced mathematics per se, but to explore whether embodied interaction within a simulated version of S2 cross E can enable non-experts to grasp some of its key spatial properties through direct experience. 32 non-expert participants took part in the experiment. The experiment started with a short Euclidean immersion aimed at familiarizing participants with VR, the controls, and the tasks. Then, they would receive an out-of-VR introduction using physical objects before going to the non-Euclidean immersion made of a free exploration phase before evaluated tasks. After the immersion, participants completed out-of-VR evaluation tasks before taking part in the semi-structured interview. Participants engaged in exploratory tasks designed to reveal geometric features of the space, such as the behavior of visual echos and the relationship between angles and area of triangles. Let's talk about visual echos. What we call visual echos are multiple images of an object, which may be distorted or attenuated. These echos appear naturally in S2 cross E because several rays of light can travel between the observer's eye and the object. We are familiar with this behavior in our physical world when we use intermediate media, such as mirrors, puddles of water, etc. For example, here, the yellow line represents a possible path for light along the Euclidean component. In blue, another possible trajectory which goes around the cylinder once. In red, another trajectory which goes around the cylinder twice. Another one in green which goes around the cylinder 3 times, and we could go on like this for a long time, because in theory, there are an infinite number of possible paths between the eye and the object, and therefore an infinite number of images of the object. In practice, paths that are too long do not allow enough light to reach the object for us to see its image. Furthermore, in the experiment, we used a rendering distance shorter than the distance at which light naturally fades, so that we could place several objects in the scene without overloading computer and the user's field of vision. Enough talk, this is what it looks like when you're inside. So here the camera is moving forward and each object has a different color. Participants were immersed in a scene like this one, with the ability to toggle object visibility, and had to try to understand how visual echos work. When they thought that they had understood, they were directed to another scene of the same kind, but in which some objects shared the same color, and then to a scene where all of the objects were gray. In the gray scene, participants could no longer toggle object visibility and were given a task to count the number of objects in the scene. 1/3 of participants succeeded on their first attempt, and just over half succeeded within 3 attempts. In total, 78% of participants developed a good strategy for completing the task, but for those who did not succeed within the 3 attempts allowed, colors were added. Here, there are 7 objects, 2 infinite cylinders, yellow and green, 4 spheres, turquoise, purple, orange, and blue, and a section of a pink cylinder. We use the VRSQ to assess participants' VR sickness level, the attitude towards mathematic inventory to assess their attitude towards mathematics, as well as a self-efficacy questionnaire. At the end of the experiment, participants took part in a semi-structured interview aimed at gathering data on the participants' experience, strategies, the knowledge they had acquired, and their intuition. We also measured the time spent on each task, the answers to the evaluation tasks, and the number of interactions. The goal of these measures was to allow correlation tests between participants' behaviors and their performances. Generally speaking, we assessed whether participants were able to internalize and articulate the introduced concepts, and examined how this learning process was influenced by their mathematical background and attitude. Here are a few of the results. 78% of participants developed a good strategy for counting objects despite visual echos. 94% of participants were able to articulate relevant factors influencing the sum of the angles in a triangle. And finally, a particularly compelling result is that 88% of participants spontaneously identified the locally Euclidean property of S2 cross E, despite this not being introduced during the experiment. This suggests that immersive VR can enable participants to observe and interpret subtle properties of the geometry through direct experience, supporting the claim that embodied exploration can be a powerful driver of spatial reasoning in abstract domains. In this experiment, we had non-mathematicians explore S2 cross E in a learning by doing approach. The purpose of the experiment was to investigate whether they could develop an intuitive understanding of the space through immersive VR without relying on formal mathematical instruction. Participants explored a custom-designed virtual environment and engaged in a series of tasks, each targeting a specific property of the geometry. Results show that most participants were able to infer and articulate the 2 key properties showcased in the experiment, visual echos and relation area sum of a triangle's angles, as well as the locally Euclidean property that was not explicitly introduced during the experiment. Additionally, their performance was independent of their educational background or attitude towards mathematics. We also observed that participants accepted the specifics of the geometry quickly, adapted their reasoning, indicating a remarkable and unexpected flexibility in questioning their acquired knowledge about geometry. Please read the paper for more details about the experiment and the results. Thank you for your attention.